Welcome to the party.
Oh, yeah.
All right. Currently 22.2 times the WHO annual air quality guideline value. Nice. Oh, what doesn't smell great? Cancer. Don't like that. Okay, my headphones are up. How's everybody doing? Happy to be here. Go outside in this wonderful smoke and I feel glad because I bike here, but I had a bunch of PM 2.5 filters since, the last several fun years. So I was breathing through 12 layers of funness on my way here. So that's why I'm not choking right now. Otherwise, yeah, I'd be falling over, coughing my lungs out because, yeah. So today, we have exponents, scientific notation, and loops and radicals if we can get them. And a dead queen. These things happen. Not very often. They seem to live a little. Let's jump into it and see how far we can get. So last time we were playing with factoring. We did the whole bunch of factor trees. We like factor trees. Those are fun. Factor trees, of course. You start with your number. You break it down into composite numbers. So in this case, that would be 8 and 6. And it's just composite because it is a combination of multiple prime factors. Then you break those guys down as far as they go. And if you have anything further to break down, you break it down further. You basically just keep breaking your numbers down until you get to the bottom where you can't break it down anymore. Fun. Let's do a bunch of this. Not a whole lot, but I made sure we have a big ugly one because of course I did. So first up, we're just gonna break 250 down as far as it'll go. I'm cheap. If I see a 0 at the end, I usually go with a 10 as my first one. That obviously makes life a lot easier. 10 is 2 times 5. 25 is 5 times 5. So it's just 2 and 3 5s. Right, and the next one, fun one, 48,510. Because you know, I can. I mainly like doing this with giant numbers because every book I've ever seen is like, oh, obviously this breaks down into this number. Oh, maybe you could pull off 250, but you probably can't pull off 48,000 and change off the top of your head. So I'm going to do my usual. There's a 0 at the end. I'm going to pull off a 10. Now I'm suddenly worried about a 4-digit number instead of a 5-digit number. Makes life a little easier. 10, of course, is 2 times 5, but 4851. Well, if you hit one, you don't know where to go with it. Embrace Mr. Calculator. I'm looking at this. It's an odd number, so let's start dividing it by odd numbers and see what sticks. Let's try a 3. Okay, yeah, that goes in even. That's 3 and 16, 17. All right, that's fun. Well, always try the same one again, see if it goes in. It does. Okay, so that's 3 and 539. Let's try that again. Nope, that didn't go in even. Okay. So we have 539. Keep going with odd numbers. 3 didn't work. The next odd number, 5, isn't going to work because it doesn't end with a 0 or a 5. Let's try 7. 7 and 77. All right, I'm feeling pretty good about that. And then 77 is 7 times 11. So we end up with 2 3s, a 5, 2 7s, and an 11. Whenever I do this sort of thing, I always make sure to keep it straight. I always go from the smallest and work my way up. You could start from the top and work your way down. The main reason I do that is just to make sure that I don't lose anything. So once I get to 5, I'm not looking at anything that has a 2 or a 3 in it. Okay. Okay, number 3 says demonstrate that the prime factorization of 126 is the same as the combined factors of both 14 and 9. Okay. So we have 126, 14, and 9 that we're looking at. And it says that we're going to demonstrate that the factors of this end up being the factors of these, because 14 times 9 is 126. So assuming that, you know, our factors are all multiplied together, you know, the whole commutative and associative properties mean that all the factors multiplied together in any orders, they'll result in the same number. It should result in the same thing. Let's see what happens. Let's say this is 2 times 63. That's 3 times 21. And that's 3 times 7. So we got a 2, a 3, a 3, and a 7. Over here we have 14. That's going to be 2 times 7. And 9 is 3 times 3. So it's also a 2, 2 3s, and a 7. So however you multiply out any of these particular factors, it's going to result in 126. You could very well have the 2 times 3, so a 6 times 7 times 3, 21. I guarantee you that's 126 because it's just the exact same prime factors put together a little differently. And actually, once you get to harder factoring with polynomials, hello, welcome to the class. Once you get to harder stuff with larger polynomials and such, and you have to start breaking numbers down to see what fits where, this is actually a useful skill I've used because honestly, I am not a big fan of sitting there with a calculator and trying different numbers all day. So I have 100% just made factor trees and put stuff together and see what sticks. That's actually a pretty useful strategy on things. Okay. I'm assuming we're feeling pretty good on that. Okay. So the next thing we hit was greatest common factor, least common multiple, and of course, lowest common denominator is effectively the same as least common multiple, just in a fraction. The greatest common factor is defined as the largest number that is a factor of all the involved numbers. So basically, it's the biggest thing that can go into all your things. That is 100% how I think of it. That is in my head somewhere. It's the biggest thing that goes into all the other things. It's a terrible way of looking at it, but in my head, that makes it a little easier for me to understand because that kind of defines it as being smaller than each one, at least. So that kind of helps me because it's easy to confuse greatest common factor with least common multiple. Least common multiple of 2 or more numbers is the smallest number, non-zero, that is a multiple of all the numbers involved. So the least common multiple of 12 and 9 would be 36 because out of all the multiples of 12 and 9, the first one they have in common is 36. It is exactly what it's referred to. It is the least, so the smallest common multiple between your numbers. And the lowest common denominator is the exact same thing, just applied to the bottom of fractions. So if you think about having to add 2 fractions like 1/2 and 1/3, you know that you can't magically knock those down to a smaller number that they both end up. You end up having to kind of beef them both up to the first thing they both have in common. So if you have that idea down, then you got the idea of down before or with least common multiple. Okay, so of course I have a bunch of problems. Unlike last time, we've already done both greatest common factor and least common multiple. And we know that the method of finding them both is the same. So I figured, hey, why not just find them both for all the problems? I went with particularly not painful examples. Because remember, the thing we're after here is not how to pull off every problem that you see in the class. The idea that we're after is getting the concepts down. So being able to get thrown a bunch of random numbers and being able to find one thing or another thing about them, depending on what you get asked, that's pretty much our goal. In this case, we want greatest common factor and least common multiple of all of these things. So we learned last time that we're going to factor each and every one of these as far down as it'll go. Break down my 9s, couple of 3s. It's a random thing that I shouldn't say out loud, but I just realized that I planned on going to KFC for lunch and I didn't. Now I'm sad, very hungry. They have really good chicken sandwiches. If you haven't been to a KFC in the last couple of years, because before that they sucked really bad.
What about that new place?
Huh?
That
Oh, Chick-fil-A?
I've never. Oh, it's not that good.
Everybody's obsessed with it, and I don't get it. First of all, the company is a bunch of jerks, and second of all, I am fully willing to set aside my morality for tasty food because that is literally my driving force in my life. And I went there and I had it, and I'm like, it's okay. Like it's not amazing. I don't know why people. It's like when everybody was ranting and raving about how great Five Guys was, and I went there and I was like, this tastes like ground beef. Like I could have made this at home.
Yeah, exactly.
I am down for the giant bag of fries. Don't get me wrong, but the burgers were nothing to write home about. But yeah, KFC has these freaking chicken sandwiches, and they give you like this giant hunk of chicken and just throw it in a bun. It's like, there we go. And they have a spicy one. It just has spicy sauce. I don't know what it is, but I need to figure it out because I'm gonna put it on everything.
Well, don't they have like a chicken breast, the chicken breast as the, I don't know, I seen that ad or something, as a bun instead of the.
I'm kind of down for that. Yeah, no, honestly, the freaking chicken patties they use are like the size of like a chicken thigh, I would say. So obviously no bones, because that would be a horrible sandwich. All right, I'm done talking about food. I'm easy to derail. This is the problem of having really bad ADHD and having to teach a class. I'm going to start randomly ranting about one thing or another thing. Okay, so we have our factor trees set up. We have our numbers down here along the side. I like to put them in ascending order, so the smallest to largest, just kind of to keep things straight. You'll notice that 90% of what I do is just to keep things straight. Because math sucks a lot less if everything is neat and orderly and you're not lost and confused about what to do because everything's a jumble. So I try to undo that jumble. So each and every one of these, remember, we are going to take the factors of these numbers, and each of those individual factors is going to get a column. So we're going to basically have all of them written out, but for each individual factor, like say another one of these would have a 7. If it had a 7, I would put the 7 here. If it had a second 7, it would need its own column, etc., etc. Now, in this case, that's not going to happen because the next one is 99. That's 3, 3, and 11. So we can't put any of those factors right here because this column is only for 7s. This column is only for 11s. Well, I got one. I got one 11, but we have 2 more 3s to worry about. So each of those is going to get its own column. That way, each row is still the factors that make up the number, but each column is the factors that are unique to those numbers. And then 121, that one's 11 times 11. Obviously, we still have that 11 in common, but we don't have another 11 spot, so we make one. Okay. Reason that I like teaching greatest common factor and least common multiple at the same time is because they're so easy to do at the same time. It's so easy to see the difference between the two when you're doing them both, because you have the same numbers, so it gives you a good frame of reference. So the greatest common factor is always, what do they all have in common? Well, the only column that's filled out between all of our numbers is 11. So we don't have anything to multiply or anything like that. We just have an 11. If I had more numbers, we would multiply them together, but we don't. For least common multiple, however, This is the largest thing that goes into each of these numbers. And I feel like we could have reached that conclusion pretty easily without going to these lengths. But least common multiple, little trickier, right? But once you have it in this grid, kind of no way to get it wrong at this point, because you take one item from each and every column. That way, the factors of each of our numbers is represented. For 77 was 7 and 11. Yeah, we got those. For 99, it was an 11, 2 3s. Yeah, we got those. And then for 121, it was 2 11s. Yeah, we got those. So because all of the factors of each individual number are represented, we know that this is a multiple of each of them. Now, what is that multiple? I don't know. It's 121 times 9 times 7. It's ugly. I don't want to, you know, if I was actually applying this to something, well, I guess I wouldn't say I'd hate my life, but it'd be a lot of writing, right? One thing that you get kind of used to as you go further in math is that you end up with a bunch of decimals on almost everything, and you just kind of have to roll with it. So it's not uncommon to have 4-digit numbers everywhere. It's a little annoying, lots of writing, but the concepts are the same. So in this case, our greatest common factor is 11, but our least common multiple is 7,623. So as I've said before, one thing you technically can do is you can start listing each of these multiples, but I mean, that's going to take a while, right? Because 77 goes into 7,623 99 times. So I am not listing all those out. No, thank you. So this works pretty well. And as I've said before, another option is to look at all of your factors here, start with the smallest number and say, okay, 3. Which of these terms has the most 3s? This one, it has 2. You can take those 2. The next number up would be a 7, right? This one has 1. Nobody else has any. So we need that 1. And then the 11s, this one has 1, 1. This guy has 2 of them. So we would need 2 of them. So you go with the highest amount of each individual factor that any of your terms has. And you obviously reach the exact same conclusion. And you can eyeball that, but again, it's kind of hard to teach eyeballing that. So until you can see it, big ugly grid. Once you see it, you don't have to do the grid. Okay? Any questions on this problem? Yeah, I don't have a question for me either. Let's do a bunch more. And by a bunch, I mean 2. So the next one, we have 8, 18, 28, and 48. This one, I'm going to do a little differently. I'm still going to do the grid thing, but kind of like how I did this right here, where I just kind of eyeballed my factors. I'm going to do that first. I'm going to do that first and see if you guys can follow them. But I'm still going to do both ways. So we factor everything as far as it'll go. 8 is 2 times 4. 4 is 2 times 2. So 8's a bunch of 2s. Fine. All right. 18, that's 2 times 9. And 9 is 3 times 3. This is going great. 28, 2 times 14, which is 2 times 7. Cool. And 48, 2 times 24, 2 times 12, 2, 6, and 2, 3. Now, one thing you might notice about how I did this is there's a couple of different ways I could have gone about it. One way is I could have looked at 28 and said, oh, that's 4 times 7. And then I would have just had to break down the 4. 48, I might have looked at that and say, hey, I know that's 4 times 12 or something like 8 times 6. You could have done that and break them down. But what I ended up doing was I ended up going with the smallest number each time. Kind of looks ugly on a paper. It kind of ends up with this like slant going. But the nice thing is that I am not looking all over in branches of trees. So I kind of do it that way a lot when I'm doing uglier ones. Just, again, it keeps things straighter. So let's say we were looking right away for the greatest common factor and the least common multiple. Greatest common factor is what they all have in common, right? So let's look at this. There's 2's everywhere, right? So what's the smallest amount of 2's we have? This one has 1, right? This guy has some 3's as well. Do any of the others have 3's? This one does, but the other 2 don't have that in common, right? So what do they all have in common? At max, just that 1, 2, because that is the smallest amount of that factor we have. I can't fit a 4 into this 18, right? So the biggest thing I could possibly pull out all of these guys is a 2. Now, if I looked at least common multiple and I decided, okay, well, let's see, let's look at our factors and we look at it the other way. What's the highest amount of each factor that anybody has? So when it comes to the 2's, this one had 1, whoop-de-doo, but this one has 3. This one has 2 of them. This one has 4 of them, right? So we go with the largest amount of those 2's. We go with the 4. And again, that's because those 4 2's would cover those 4 2's. It'd cover these 2, it'd cover that one, it'd cover these 3. So each of those terms, at the very least, their factor of 2 can fit into all, right? Well, the factor of 2 on this guy. These will all fit into that. Then our next term up would be a 3. This one has 2 of them. This one has 1. So we go with the highest amount, which again is 2 of them. It helps if I write the right number. A little bit. That's a 3. The 3, so we got those 2 covered. The next number up would be a 7. There's only one of them hanging out here. So do we need anything else? 4 2's and a 3, 4 2's and a 3, that fits. 2 2's and a 7, 2 2's and a 7, 1 2 and 2 3, 1 2 2 3, 3 2's. Yep, that definitely covers. So this covers all of this, right? So our least common multiple is always kind of a bigger, uglier number. Okay, so if you multiply all of that together, we end up with 1,008. So again, that's one way of doing it. If you can feel comfortable doing it this way, then more power to you. That's all you really got to worry about. If you're not comfortable with it, then we do our tried and true grid thingy. Gonna call it grid thingy. That's its name now. And you just work your way up. 8 is 3 2's. 18 is a 2 and 2 3's. 28 is 2 2's and a 7. And 48 is 4 2's and a 3. 2, 3, 4 and a 3. So we get a range like this. Greatest common factor is whatever they all have in common, that 2. Least common multiple is one item from each column. You're very unlikely to get everything in a nice, neat, orderly fashion right there, but it still works, right? We have the exact same factors here as we do here. So this would also end up being 1008. The worst case scenario, you don't understand what we did here, we got that. That's always good to rely on. Your brain turned off, you're sitting in a test, you're like, oh God, I can't think straight. Do this. It's a little simpler. It's time consuming, it's kind of ugly, but it gets the job done and it's hard to make a massive mistake. So that's why I roll with it. Okay. Let's do something with 21 again. Okay, whatever. Past Ben, you're an idiot. Okay. Okay, so in this case, we just have these 3 numbers. So when it comes to the factor trees, I'm going to do this just for good measure because, trees. But 11 is just an 11, right? That's not going to do anything for us. 121 is 11 times 11. And 143, I don't have a clue. 143. Try an odd number. Nope. Nope. I'm not going to try 9 because if 9 worked, then 3 would have. So you think of the next prime number. Guess what that is? Oh my God, it's 11 times 13. Who would have guessed that this was going to have an 11 in it? What a surprise. So what's our greatest common factor? 11, right? Yeah. Because it's the only thing they all have in common. The greatest common factor is at the very most your smallest number. At the very most. It's not going to be above it because I can't fit a 20 in there, I can't fit a bigger number than 11 into 11. So that is the largest your greatest common factor can be. By comparison, the smallest your least common multiple would be the largest number that you have. Because if the other 2 fit nicely into there, then you'd be done. Now that doesn't seem to work out too great, right? But it's a possibility. So we would do our usual grid thingy. And you'll see why I did the 11 with a little line as if it had a tree, because 11 is just 11, right? So I'm just doing that part to keep everything straight. 121 is 11 times 11, and 143, 11 times 13. So 13 gets its own column. Okay. Their greatest common factor, again, just 11. It's the only thing they have in common. The least common multiple, however, one item from each column, we end up with 11 times 11 times 13. Not the prettiest. So I have 1,573. Never would have guessed that. Not too bad, right? Totally doable. Nobody's freaking out. No questions. So let's look at the others. These are going to be similar. So for number 4, find the LCD and combine. Now, one thing I always thought was really interesting is something I've actually noticed it after years of tutoring, and it's just kind of fascinating because I would go over least common multiple, and I would always end up with at least a few people with their eyes glazed over in confusion. Always. But I could show them a fraction like this and ask them what my common denominator should be. And usually, they might not be able to tell me outright, but even if they couldn't, they'd have an idea, right? Now, in this case, what is it? Other way around. That would be the greatest common factor, but if I am trying to add these guys together, I need a common denominator. So the other way around. We need to have the smallest thing that they all fit into. So we got 25, 125, and a 5. I know that 5 goes into 25. Does 25 go into 125? Yeah, right? You got 5 quarters? That's about 25. Cool. So our lowest common denominator is 125 because it's the smallest number that they all fit into. So that is the exact same, that's the exact same amount of math or exact same process of math that doing this big ugly chart and doing this is. Because you've been doing this longer, it's easier to see. You have a frame of reference already. Now, if I threw giant horrifying fractions at you and told you to combine them, well, then we'll probably go back to one of those charts. I'm not above it. Okay, so if I'm going to combine all of these guys, I need to have a common denominator. At this point, I'm just rewriting it. So to have a common denominator, to get all of them to that 125, what would I have to multiply this by? 4 out of 25. Well, I need 5 times that bottom. So I have to multiply this by a 5 down here. And in order to get away with that, I have to multiply by a 5 up here. That way I'm multiplying by an ugly looking 1. And you can multiply anything by 1. So it's a cheap tactic, but it works. 6 over 125, we already have the common denominator. We don't have to worry about it. That one's good. And then 3/5. Well, this one needed the 5. This one's going to need the 25, right? Same idea there. So wherever we have multiplication, we multiply across. That's going to be 20 125ths minus 6 125ths plus 75 125ths. Not the prettiest numbers, right? Then you can combine them however you want. We have a 20 and basically a -6 and a 75. So if you're more comfortable putting the 20 with the 75 first and then subtracting 6, cool. If you're more comfortable doing 20 minus 6 and then taking that and combining that to the 75, also cool. Both completely valid things that you can do. You can even combine these two and then bring in that 20. Doesn't matter. No matter what you do, you always are going to end up with the same number, right? So we end up with, I'm personally going to do the 20 and 75, so I get a 95 minus 6. That's going to be 89. So 89 out of 125. Now, whenever you do problems like this, see if you can reduce at the end. Now, assuming that we got the actual lowest common denominator, not just a denominator they go into, our canceling should be minimal. Now, in this case, I know 125 is just a bunch of 5 stacked on top of each other, right? Is 5 going to 89? So this isn't going to reduce at all. But always look to see if it can. Because that is one thing that always catches people. You're not thinking about reducing fractions because you're thinking about combining them. But that's always a step that's going to be there. Our next one, we have negative 14 out of 21 plus 1 out of 3 plus 12 out of 70. So there's actually a couple ways to do this one. Let's just go with it right out the bat, what we have written right here. Let's do it that way first. Then let's see if we can clean it up and do it another way.
When you reduce it.
Good. That's what I'm gonna do. Don't jump ahead on me. Don't jump ahead on me. No, it is. But yeah, you totally do that. Welcome to the party. Don't forget to sign in. I forgot to print off a sign-in sheet, so we're using the other side of Tuesday. All right. So if I was looking for a lowest common denominator, looking at my factors again, I have a 3, a 7. This one has a 3. This one has 2, 5, and 7. So nothing has multiples of anything, but if I wanted an LCD, I'd need at least one of every factor, right? So I would need a 2, I would need a 3, I would need a 5, and I would need a 7. So we multiply those guys together, we end up with 210. And this is where I could get my common denominator. Rewriting it just to get us to that point. So that first one, I'm going to multiply by 10 over 10. This one by 70 over 70. And this one by 3 over 3. Multiplying across, we get negative 140 out of 210 plus 70 over 210 plus 36 over 210. Now again, I can combine these however I want. Here's a cheap way of doing it. Just throw it at a calculator and see what sticks. Negative 34. So we get negative 34 on top and 210 on the bottom. Now, does that reduce? Yeah, right? Because both the top and the bottom are even numbers. So if I chop them in half, then I can ask myself if that reduces. Well, no, 17 isn't going to go into 105 at all. 17 I can't break down. So that's as far as we can go. Now, yes, I could have done this a different way. I absolutely could have. Let's look at another way. Let's kind of get that into the frame nicer. Here we go. So just another way of doing it. Yes, you can in fact reduce now. We reduce now, we would get negative 2/7 plus 1/3 plus 6 out of 35. Now, is this going to make our lives much easier? Well, we wouldn't be dealing with quite as large numbers, but we still end up with 3, 5, and 7, right? So that ends up being 105, right? And I'm doing it this way because, hey, 105, that sounds familiar, right? That was our denominator down here. So if you are on a test and you start doing your work and you make it to the middle of a step down here and you're like, I should have reduced. Don't think I am wrong and erase everything and start over. Think, okay, if I didn't reduce here, then I'll just have to reduce at the end. If I reduce it first, we're probably not going to have to reduce at the end, right? Okay. And just for good measure, I'll finish it off. So this one, I would have to multiply by 15 over 15. This one, I would have to multiply by, what, 35 over 35? And this one, I have to multiply by 3 over 3. I would end up with negative 30, 105, plus 35, 105, plus 18, 105. I think I broke something. I feel like I broke something somewhere. No, I broke something. This doesn't end up getting the same thing. That gets me 23. How am I off by 40? The hell did I do? I see what I did. That's not 2/7. That's 2/3. Oh. That's a big mistake. It's always easy to be able to see what you did wrong if you do a problem twice. Do I recommend doing every problem twice? No. But that definitely changes our answer. Because that changes what I have to multiply by. I should have multiplied by 35 right there. That would have been 35 over 35 there. I would have ended up with negative 70 plus 35 plus 18. So we would end up with a negative 17. Like, man, I screwed something up, but I don't know where. That happens. why I say, if you see me make a mistake, don't assume I know more than you. You might get something stupid. What's up?
How can you find, how can you find 105?
So over here, I found the lowest common denominator by looking at the factors that we have in each denominator. Now, it worked out either way in this case, even though I made a big mistake. But since each of these had a 3, and then this one had a 5 and a 7, then our LCD would have to have at least that 3 and a 5 and a 7. That way, each of these denominators is covered because this one had a 5 and a 7, that's covered. Each of these had a 3, that's covered. So each of these denominators can now go into this number. So as long as we set it up that way, we end up with our lowest common denominator, and we can beef up all of our denominators up to that point. And then they're like terms, and you can put stuff together. And other than me screwing up, anybody have any questions on that one? Cool. So that's the end of my review stuff. Let's get to new stuff. I like new stuff. You like new stuff. You might not actually like new stuff, but you're kind of my captives for 2.5 hours a couple of times a week, so you like new stuff. So, exponents. We poked at a couple of them, but we haven't gone into them. They really only have so many rules of putting them together and how they fit together, that once you get down the couple of rules, you just kind of look like a wizard when you're doing complicated looking math with them, but they're not bad. Exponents are literally just shorthand for repeated multiplication of the same thing by itself. So in this case, 5 times 5 times 5, you would say that's 5 to the 3rd. The exponent, the number that's up and to the side, that guy is saying, I have that thing that many times. So I have that 5 3 times. The process of using exponents like that is called raising to a power. So the exponent is the power. So this expression is actually pronounced 5 raised to the 3rd power, or more commonly, you'll run into just people saying 5 to the 3rd. So that's one thing that's always fun because, well, as I've said, I've tutored a lot. And if I have somebody tell me what their problem looks like out loud and I'm copying it along, and then I look at theirs and I look at mine, I'm like, these are very different things. It's kind of useful to have some of the terminology down, right? So in this realm, there's literally just 2 specially named powers because you use them so often. So the second power is usually just pronounced squared. You're squaring the number. The 3rd power is usually pronounced as cubed because 3 dimensions is a cube. So 5 to the 3rd is commonly pronounced as 5 cubed. And also in mathematics, the caret symbol, that little upturned thing, is used to represent an exponent, such as an exponential power like square or cube. So you might see 5 raised to the 3rd power written as 5, a little caret, and 3. And you'll actually see that decently often in my notes, just because it's easier to type. There's some decent shortcuts in Google Slides to do exponents, but you know, sometimes it's annoying to jump into the exponents and then jump out. So working out exponents can be quite simple. So seeing 5/3, we can break it down into a bunch of fives multiplied together and we get 125. So if you want to go the other way, breaking things down into an exponential form, that's one application of the factor trees that we were doing. You would take 125, find its prime factorization, and say, oh, this is a bunch of fives. So instead of saying 5 times 5 times 5, you could say that's 5 to the third. Now, as a quick example, let's look at one of our earlier problems. Number 2 that we did earlier for the greatest common factor and least common multiple. Another way to have written this least common multiple would have been to say, oh, I have 4 2s, that's 2 to the fourth. I have 2 3s, that's 3 squared. And I have a 7. You can kind of put a multiplication symbol in between. Whether you do or not, that's another story. But that's a nicer way to write it rather than writing out 2 times 2 times 2 times 2 times 3 times 3 times 7. You can say 2 to the fourth, 3 squared, 7. Makes life a little nicer, right? Also a heck of a lot easier to work with. So they're very useful. Well, let's do some of this. So these problems are pretty quick. We only have 9 of them, but we're basically just going to be going to an exponential form on the first couple, and then we're going to be converting back into integers on the next couple. So I'm going to go ahead and write a ton of these down. So we're just converting the first couple to exponential forms. So I got some nice, neat numbers, and I got some not as neat numbers, just so you can see what you do with both. So 27, we could just factor tree that. 3 times 9, which is 3 times 3, right? So 3 times 3 times 3, what is that? 3 cubed, right? Because we have a 3 times. Number 2, it's a 4. We know what that multiplies from, right? So in this case, it's 2 squared because I have 2 cubed. Now, is it cheap that I did 3 3 and 2 2 and the same couple of numbers? Yeah, probably. Well, let's do some more fun stuff. About 343. I don't know what that is, right? So, embrace Mr. Calculator. Let's try dividing by 3. Nope. Let's try dividing by 7. Ah. So that's 7 times 49. And 49 I know is 7 times 7, right? Okay. So if I have 7 times 7 times 7, that's 7 3 times. 7 to the third power, 7 cubed, however you want to say it. Just get your exponents. Now, On number 4, number 5, we got things that aren't perfect powers. What do we do with those? 72, that one's 2 times 36. 36 is 2 and 18. 18 is 2 and 9. 9 is 3 and 3. I didn't give myself enough room, so it's kind of cramped in there. So we end up with 3 2s and 2 3s, right? Okay. So what you end up doing is you just write the term you have, then give it its exponent. So this one has 3 of them. And then it's kind of like with variables. With variables, if you have a number right next to the variable, that implies that it's multiplied. That's going to work out the same way with these exponential forms. I can just say that I have that 3 2 times. And the fact that I can see that each of these has its own exponent, I know, okay, this is a unique term and this is a unique term. And since they're right up against each other, that means they would multiply together. Okay. Now you could put the multiplication symbol between them. You don't have to. And in fact, most of the time in a book, you're going to see it without that. But one thing I will say is that if you have something that doesn't magically have an exponent, like earlier we had the one with the 7 or the 7. No, I'm losing my mind. Whatever. If you had something else and it was there, you just had one of it. It would be safe to put at the end, but then if I had another thing, well, I kind of have to put that multiplication symbol, right? Because I can look at the number 72 and say, I fully recognize that that's not 7 times 2, right? So it's all about making sure that we don't have something that's kind of ambiguous. This is good. This is good. It's cool either way. Now, number 5, we have 900. Let's be cheap about this. What do I like to do with zeros? That's 100 times 9. Well, that's awesome, right? 100 is 10 times 10. 9 is 3 times 3. But the 10s each break down further. That's 2 and 5. That's 2 and 5. Okay, so what do I have? Well, it's kind of a jumble, right? We have 2, 5, 2, 5, 3, 3. Well, start with the smallest number, 2s. Say how many you got. We have 2 of them. Next number up is 3. Say how many you have. 2 of them. The next number up is 5. Say how many you have. Also 2 of them. So we end up with 2 squared, 3 squared, 5 squared. Is that prettier than saying 900? No. But it has its applications. Being able to switch between them is a useful skill to have, and these are the good kinds of problems that kind of force you to understand them. Okay. So now we're going to go the other way around. The other way around is not bad as you would expect, because you're just going to look at them the other way around. I always like going over this. Some of you might be like, this is obvious. Some of you might not. But I've seen too many students look at this and say this is 7 times 2. And I've seen that a lot. I've seen that a lot. So that is why I like to do this stuff, because if that was an inclination that any of you had, not what you do. We have a 7 squared. That means I have 7 multiplied by itself 2 times. So it's 7 times 7, which is 49. Speaking of more 7s, number 7 down here. we have 4 to the power of 3. That means we have 4 multiplied by itself 3 times. Anybody know off the top of their head what that is? 64. I know that off the top of my head because for some reason, 4 to the 3rd power seems to pop up a lot and like higher math problems. I don't know why. I don't know why I've done 4 to the 3rd so often, but it seems to be a popular number that they throw into math books, so that's why it's here. Then 2 to the 4th. Anybody know what that is off the top of their head? This is one reason that I like to go over those commutative and associative properties so much, because this is actually pretty quick. Yes, I could do 2 times 2 and then multiply that by 2 and then multiply that by 2. Or I could look at it as I'm going to combine those guys. Yeah, exactly. I'm going to combine those guys, and now it's a 4 times 4. Easy, right? So if you break things down into their factors and kind of pick and choose which ones to put together, sometimes that makes your work a little bit easier. Could you just throw it at a calculator? Yes, but I don't want you to. That one you could do, you can totally do. You just got to think about it for a minute. So number 9 is 4 to the 3rd, 2 to the 4th. Gee, I wonder what this breaks down into. Now, yeah, you are correct. Now I did this intentionally because we just did 4 to the 3rd and 2 to the 4th, right? So 4 to the 3rd, 2 to the 4th implies that these multiply together, right? So if I know this one is 64 and I know this one is 16, I can just multiply those two guys together and we get 1024. And you know what? Let's take this example a little bit further because I don't have slides prepared for it, but sometimes you end up having to, you get given something like this and you get asked, write your answer in simplest exponential format, something like that. And you basically have to clean it up. Now, one thing I will say is, well, 4 to the 3rd, 2 to the 4th. Just did 4 to the 3rd, right? It's 3 fours. Well, if it's 3 fours, how many 2s is that? 2, another 2, another 2. That's 6 2s, right? So I could also write this as 2 to the 6th, 2 to the 4th. And you know what's going to end up happening? Those are going to combine. If I have 2 multiplied by itself 6 times, and then I also have it multiplied by itself 4 times, how many 2s do I have total? I got 6 of them, and I got 4 of them. I got 10 of them. So this guy you could actually break down to 2 to the 10th. Perfect power of 2, 1024. Every time your computer has a kilobyte or kilobit or megabyte or megabit, it is not in thousands. They round it off when they're selling you stuff. And that's why if you buy a 1 terabyte hard drive or something, you plug it in and it never says it's a terabyte because they are rounding that sucker off and the computer knows it's 1024, but they're selling that thing in thousands. How are we feeling on this? We're feeling okay, bouncing back and forth on exponents. Not terrible. Nobody's shrieking. I'm happy with this. Let's look at more stuff. Now, we just did this specific thing on that example I have, multiplying exponents. Now, you can always do this when they have kind of the same base. They have the same integer that's being raised to a power. You can put those together. So for example, here we have 3 cubed multiplied by 3 to the 4th. Now, since both terms have the same base, that 3, you can actually just add the powers together. So if you have a total of 3 of them multiplied by a total of 4 of them, you're basically just saying how many you have multiplied together all at once. So you have 3 cubed times 3 to the 4th, add the powers, 3 to the 7th. So down there, if these terms did not have the same base, for example, 3 cubed times 2 cubed, we would then need to work out what each of them is and multiply them together, because what else are you going to do with that? You can't put them together if they have different bases. Let's do a bunch of math, right? These ones are pretty quick. And if you notice, the way I have 4 written is a way that sometimes you might see exponents written, say, in certain math texts. If you're thrown off on anything in math in the future and you're stuck Googling it, figuring it out that way, because let's face it, everybody does that. That's another way you might see it written. So I wanted to give it as an example. So these are all pretty quick, right? The first one we could do pretty quick, because we have 3 2s and 6 2s. They're multiplied together, which means how many 2s do I got? 9, right? 3 and 6 is 9. We have 2 of the 9th. And then number 2, if we have to write this in an exponential form, then we need to break everything down into exponents. I am not going to factor tree of 25. We know 25 is 5 times 5, right? I don't necessarily need that set of parentheses there, because the parentheses, all that's really telling me is that I have this thing kind of off to the side of here, and that's multiplying onto that. So if I write it in such a way that I recognize that multiplication's happening and I'm not losing anything by losing those parentheses, then I can just drop them, because they're not doing anything for me, right? I could put each of those into a set of its own set of parentheses. It's not going to make a difference. Okay, so I have 5 squared times 5 squared, 2 5s and 2 5s. That's a total of 4 5s. And then number 3, we have 3 cubed times 2 squared times 3. Who knows what to do?
3 to the 4th times 2 to the 2nd.
You are correct, sir. Now, one thing I do want to cover is that I usually, if things don't have exponents, and you're doing math where exponents are involved, I see a lot of people not count anything with an exponent. But how many 3s do I have there? 1, right? So you could just kind of put a 1 there as a placeholder, just so you can see it. That way you can more easily recognize, hey, these two go together, right? I have 3 of them here and 1 of them here. So I have a total of 4 3s. This 2 squared, that doesn't go anywhere, right? We don't have anything to combine with the 2. So we could just put it next to it. That implies that it's still being multiple. Okay. And then the nice one, what's the next one? 7 squared times 7 to the 5th is it'll be 2 plus 5 is 7. 7 to the 7th power, because we have 2 7s here, 5 7s here, so we have a total of 7 7s multiplied together. Why are exponents useful? Because what we just did was 49 times 16,807, and you would have ended up with 823,543. I don't want to, right? It's a lot easier to just be like, oh yeah, there's 2 of them, there's 5 of them, so there's 7 of them. Yeah, I like that. Simple, neat. It's not horrifying. I like that way too. Okay. So we can do multiplication. What about division? So pretty simple, right? If we have 2 to the 5th divided by 2 squared, so you're dividing exponential numbers with the same base. All you do is keep the same base, but you subtract the bottom power from the top power. So top one minus the bottom. So when we're multiplying exponential things together, we add the powers. If I'm dividing exponential things together, I'm subtracting. So it's just the other direction, right? Now, that's all I got for division. I laughed like an idiot when I saw that. Just absolute idiot. The dumbest joke. And I love it so much. Okay, so I'm going to write these guys out. And I'm a horrible person with number 4 that exists. That one I'm just going to write exactly as it's written, so I can show you guys how to translate something weird like that. So one nice way of looking at these, I just want to go through it real quick. But a nice way of looking at these, and I use this extensively once you get to the algebraic forms of simplifying these ugly things. Because then you got like tons of A's and B's and C's and X's and Y's and stuff. And they're everywhere, right? They're everywhere. But what I like to look at it as is, well, if I have 8 to the 3rd, that's 3/8, right? And if I'm dividing by 8 to the 1st, that's 1/8. Well, what do I got? It's a fraction. You're reducing, right? So you can absolutely do that, and you can visually see that you're going to have 2 8s left on top, right? Because, hey, what's the book way of doing these? Well, we have 8 to the power of 3 divided by 8 to the power of 1. So you do the 3 minus the 1, and you end up with 8 squared. Now, later on, we get to really ugly applications of this stuff with variables and the bottom one being bigger than the top one, and it gets really messy. But if I look at it as canceling, that actually ends up working out really nicely, regardless of what's going on. Now, I can look at number 2 and think of it the same way, right? I have 2 to the 18th divided by 2 to the 14th. If I was thinking about this in terms of, well, I could cancel a bunch of 2's, right? There's 18 here and 14 here. How many are going to cancel? 14 on each, right? So I would have 4 left on top. Now, for the time being, I am going to write it this way because there's no way for me to directly translate to paper. You just eyeball it. But it works, right? In cases like these are, I got some big ugly exponential functions here. 5 to the 106th power is this horrifying thing that my calculator apparently doesn't get spit out an error. It actually calculated it, and I'm actually really surprised by this. Okay, it's that many digits. I'm not counting as a lot, right? It's a big freaking number. As a big freaking number. Yeah, cool. So I'm not going to write that number down and then 5 to the 92, write that number down and then divide them. What am I going to do? I'm just going to look at the exponents. Top one minus the bottom one. Why did I put a 5? Why did I put a 5? I'm playing with 5s. Top one minus the bottom one. Okay, so what's the difference between 106 and 92? You're doing it in your head. Subtraction's weird in your head. It's easier to start from the bottom one and add up. That's how I do math in my head. That's actually how they teach you to do it in Common Core stuff. Some people hate Common Core. I was like, oh my God, this is the first time I've ever seen anybody write down on paper how I do math in my head. That's why it's weird looking and geometrical and stuff, because it's literally, they're not teaching it right. It's how you're supposed to think about it. The other stuff that we've always done on paper is still easy. So this minus that, we end up with 5 to the 14th. Now, we have Big Ugly, right? How many of you are intimidated by Big Ugly? What is that? Is that concerning? Is that scary looking? Somebody threw this at you on a test. Would you even know where to start? So what I like telling people is that second you start seeing brackets, literally all that is a separate set of parentheses that's just there to show you, hey, this one starts here and ends here, right? So that's all that's doing, is it's telling you this guy's one group. So I have one group divided by another group. Okay, well, if I write that as a fraction, nothing's acting on this group, right? Nothing's in front of the set of parentheses, so I don't need it. I can just write what's inside. Now, over here, nothing's outside of these brackets, but I do have a set of parentheses inside, and something's hanging out front of it, right? So I can drop these brackets when I write this down here, but I can't drop that set of parentheses because that set of parentheses is telling us, hey, these two are multiplied together. Okay. Now, if we were just going to work this out, you might be tempted to just start multiplying stuff, right? But we're learning about exponents. What do you do when I have multiple of these things all in one problem? You do exactly the same thing. And this is actually a great example on why I don't like always writing them this way. Because if I have a larger problem with a bunch of different terms, if I have 2s, 3s, 5s, X's, Y's, A's, I don't even care, whatever you want to throw at it. If I have a bunch of those, the book way of doing it, and I'm going to do it this way, the book way of doing it is to separate it out into multiples of these. So everything kind of loses its ability to stay in the fraction. And it kind of gets weird looking. Now remember, there's one of these 2's, so we do have to subtract 1, top power minus bottom power. With 3's, top power minus bottom power, 5 minus 4. Now, what ends up happening is really nice in this case, right? That's neat, that's pretty, it's simple, but it's neat and pretty and simple because I made a problem for you guys to learn this from. So let's say I had some, we keep talking about weird, funky algebra problems. Let's do a weird, funky algebra problem, right? I'm gonna talk about it, might as well do it, right? Let's say I had, I don't care, 5 to the 7th, a squared b c cubed over 2 squared 5 to the 4th a to the 5th b, let's leave b there, and c to the, just C. Let's just do BC. There we go. Let's say I had to apply this concept to this thing. Oh my God, threw letters everywhere. Now it's a horrifying giant thing. No, it's not, because the concept is exactly the same as what's happening over here. If you can do this, you can do this. Now, the downside, that it's ugly, right? Now, particularly with this 2, when I start separating it out, like this stuff over here, what happens to that 2? Where does it go? Right? Well, that's actually something that has always bothered me because there's no answer to that. When they put these things in the math books, they don't really cover what happens when you don't have everything match up nice. So what are we going to do? If I did this the way that the math books teach it, I'm going to write it out. It's going to look ugly. I'm going to ignore it. We're going to keep going. And then I'll show you a nice way of doing it. Okay? I'm going to show you the Ben way. The Ben way of doing it clicks for everybody and is incredibly easy. And you don't have to make a giant, horrible jumble like I'm about to write. So if I was to start with the smallest thing I have, the smallest thing I have is a 2, right? Well, I don't have anything combining with it. So if I have nothing to combine with it, I'm just going to write it out. It's just going to stay there, but it's in the bottom of a fraction. Now, the complicated thing here is I'm just going to go ahead and leave it in the bottom of a fraction. Because what we're basically doing is we're separating things out by the factor and their powers. Now, this one, we haven't gotten to what to do with a power in the denominator on its own. Spoiler alert, it ends up negative. But for now, I just leave it as a fraction. I don't care. The next one up is a 5, right? We have 5, 7 on top, 4 on the bottom. So 7 minus 4 here, top minus bottom, right? Then we have an A. We have an A. And top power minus bottom power. We have a B. Well, we have one of them on each, right? Top power minus bottom power. And then we have C. 3 here and 1 here, so 3 minus 1. You end up putting all these guys together. B to the 0, end up with B to the 0, anything to the 0 power, anything to the 0 power is 1. So do I need to write a 1 here? Do I need to write that A is multiplied by 1? No, because it's there. I don't need to write that it's multiplied by 1. So the B would kind of drop. And C the second. But once you do all this, the proper way of doing it is to put it back into a big ugly fraction. Now, I haven't done it yet. Haven't done it at all. Okay, oops. So I apparently don't have a slide on negative exponents. I should, but I don't. So quick crash course. What you do at this point, should have done that, is you put everything back together as a big ugly fraction. Anything that has a positive power stays on top. Things that have, let's see as well, right? Things that have a negative power, this A to the negative third, that'll actually go on the bottom and become a positive power down there. And that's actually something that we should have down in notes, and we don't. If I have, say, I don't care, A to the negative X, I don't care, just general terms, something to some negative power, that is the same as having that something to a positive power in the bottom of a fraction. Likewise, if I have a negative power in the bottom of a fraction, that would go to the top of a fraction and become positive. So this is a useful thing. Have that in the notes if you're taking notes. If you're not taking notes, pull out your phone, take a picture of the screen right now and be like, cool, this is a thing that might come in handy. Dealing with negative exponents is a useful skill to have. Now, when it comes to this problem, we're done, but it was a lot of work, right? It was a lot of work. It's too much work. I don't like it. I don't like it. You don't like it. You can lie to me if you want to. You can say you like that. No, you don't. Don't lie to me. So let's do this a different way. I'm going to rewrite the problem down here. And believe it or not, we are going to do this in one step by eyeballing. I've told you, there's only so many rules you can have on exponents. And if you get them down, you look like a freaking wizard. So what I usually do, similar to the way of doing it over here, similar to that, what I usually do is I start from my smallest term. Usually I'll do the ones with the nut where it's just the integers, the numbers, and then I'll worry about the algebra ones afterwards. So I'm going to start with my smallest number, 2 squared, right? Is anything messing with that? Do I have another 2 anywhere? No. So nothing happens to this. So we're just going to stay put. Okay? Now the 5s. I have 7 here and I have 4 here. Let's think about that. We're going to think about that conceptually like I did up here. number one I did is canceling, right? And you can see that pretty nicely. If I have three of them on top of one of them, I can see that one of them is going to cancel out, right? And I'm going to have two left right there. I can see where they are because there's more up here. That exact concept is where I'm going to go with the rest of this problem. I'm going to look at those fives and I'm going to say, okay, I have 7 here and I have 4 here. Okay, so how many are going to cancel? We have 4 in common to both, right? So 4 would cancel here and 4 would cancel here. That would leave me with 3 right here, right? So we would have our 5 to the 3rd right there. Now our A's. Done with our numbers, let's go to the letters. Now our A's. We have A squared here and A to the 5th down here. Now the proper way of doing them is you subtract them, you end up with a negative exponent, and then you convert it to a positive exponent by flipping. The way I like to look at it is saying, I got 2 here and I got 5 here. Well, 2 are going to cancel for both, right? 2 are going to cancel here, 2 are going to cancel here. So I have 3 left right here, and that's all I got to think about. I don't have to think about, I'm going to have to move it. I don't have to think about, is my exponent negative or positive? All I'm looking at is, I got 2 here, I got 5 here, 2 cancel here, 2 cancel here. I have 3 left where the 5 was. Cool. The B's. What's B divided by B? Gone. A lot nicer to look at than, you know, this thing and that, and then dropping it that way. The C's. I have 3 up here. I have 1 down here. That 1 is going to cancel with one of these C's here. So I have 2 left on top. I didn't even need to have that much of a fraction bar. We did all of this in one step. It was a big, ugly step, right? But we took that problem, we meant, instead of writing it as many tiny little things, we took it and mentally thought about each of these breaking down. And by doing that, yeah, any teacher who says show your work is going to start pulling his hair out. But it works out really nicely, doesn't it? You're all going to forget this by the test. It's great.
Could you just rearrange it to make it simpler though, those 2, line them up? Could you do that way? Yeah, I mean, change it around.
If you don't like how it's written, you
Yeah.
can totally like line them up similar, kind of like the grid thing,
Yeah.
kind of grid them. Yeah, you can totally do that. As long as you've got, you know,
Same
multiplication symbols or whatever to show that they're connected. Yeah, you can totally do that. There's a lot of things in math that you could absolutely get away with, and nobody tells you that you could get away with it. I 100% just pulled this out of thin air one day. I don't even care. It does not, these do not have to be that hard. These do not have to be this hard. Because then you end up with this weird, ambiguous, what do I do with the 2? You know what they actually really wanted you to do with that 2? They would have wanted you to say that I have none up top and 2 on the bottom. You would have had a 0 minus 2, you would have had a negative 2 right here, and then you would have changed it to a positive 2 and dropped it to the other side of the fraction bar. Now, am I going out of my way to avoid those negatives? No, I'm not. Being able to deal with negative exponents, again, this block, useful concept. You have a negative exponent, jumps to the other side of the fraction bar and becomes positive. That's it. They always teach it as 2 separate rules. It's complicated looking, it's confusing. Doesn't need to be. You have a negative exponent, throw it on the other side of the fraction bar and make it positive. You don't have a fraction? Cool, make it a fraction. Put that sucker under a 1. Call it good. Okay. Okay, so how do we feel about dividing exponents? Happy, giddy? Giddy's a good one. We can go with giddy. I'm not getting kids that's telling me they're not giddy, so yes, you could logic it into be not that showing there's giddy. Not telling me not. Okay. Let's do some more stuff. What if we have exponents with an exponent? What if I have exponents outside of a set of parentheses? Well, if we remember, by putting up something in parentheses, we're saying that's a thing, right? If I have an exponent outside of that thing, it's telling me I have that thing multiplied by itself that many times. In this particular case, I would have an x cubed 6 times, right? So I have 3 times 3 times 3 times 3 times 3 times 3. I had to stop and count how many I'd already done out loud and go back. That was awkward. So what you can actually end up doing is you could say, well, if I'm going to have those 3 6 times, this is where you multiply. This is where you multiply. And in fact, if you're ever doing like a test where this is a concept and you need something on a cheat sheet, usually that little example right there is probably all you're going to need, right? Like I said, if I add x squared to the 4th power is outside of the parentheses, so it says you have x squared multiplied by itself 4 times. You could write them out separately. X squared, x squared, x squared, x squared. They're all multiplied together, so you would add the powers, 2 and 2 and 2 and 2. That gives you an 8. But like I said, if you have a power outside of a set of parentheses, you just multiply that sucker into the parentheses. And if you had multiple terms inside of that set of parentheses, distributive property kicks in. You have to multiply that exponent onto all of them. Do I have that as an example? Tell me I made an example like that. Oh, you betcha. I just love that comic so much. It's so stupid. Why do you call them the Dark Ages? Because of all the knights. Try to get his head lopped off. Get it? It absolutely seems like something I would do in my last moments, is make a really stupid. I'll probably go out with a pun. Makes me ecstatic to think about it. Get it? Hey, hey. That was particularly bad fun because we're not dealing with eggs in any way, shape, or form. Okay, so we have 2 cubed raised to the 2nd power. All you need to do is multiply those powers together, right? We end up with 2 to the 6. That's it. We're done. That's great. I like it. I like it. You like it. Everybody likes it. Number 2, we have 3 squared to the 2nd power. No complicated math here. I don't even care that that's a 3. All I know is it's a thing. I got 2 of it. twice. Multiply them together, you get a fourth. 3 to the fourth, that is 81. Need to know that? No. All right, this one I went parentheses happy. I always like to go a little parentheses happy on these types of problems because, I mean, you could do one and not have a problem with it and do it over and over and over again. And then they throw one more layer on it and you're like, oh God, what do I do now? Okay, so easiest thing to do applies to all math, not just this. You got something complicated looking, start from the inside, work your way out. So we have 3 squared, and that thing squared. Okay, ugly, weird, don't like it. Is there a special rule here? I don't know. Do enough of these, you could probably make one up. But what's going to happen? Well, let's leave this one alone and worry about what's inside. If I worry about what's inside, oh, that's awesome. That's the last problem, right? That's 3 to the fourth. Oh, well, that's awesome. I could do that all day, right? So I can multiply these powers and end up with 3 to the 8th. Now, can I look at this as saying I can multiply all these powers together? In this very particular instance where I have one number that has a bunch of exponents for no good reason, yes. Am I going to explain that as a rule? No, because you're not going to run into that very often. What you're going to run into more often is nested little sets of parentheses where things get ugly and weird looking. And the easiest thing to do in every instance of that is go the furthest in and try to work your way out of it. Every time. Don't care if it's this, don't care if it's algebra, don't care if you get up to like calculus 3 and start doing stuff like that. I guarantee you that concept gets applied in Calc 3. Number 4, I have in one set of parentheses for the record, a squared b to the 5th, and that is raised to the 10th power. Raised to the 10th power. Okay. So again, I want to go on with this one by saying we have to consider the distributive property. I have the 10th power of everything in that set of parentheses. Now, I will say this only works exactly this way if these things are multiplied together. If there's a number, if there's a sign in between, like a plus or a minus, we ain't there yet. And you know what? I hate those. So if you really want to know, you really want to see something ugly, here, I'll show you guys something. This is why we're not putting a sign in the middle. Da, 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 da. You start playing with weird triangles of coefficients. Ugh. Yeah, I've had to do this. This is not pretty. I hate the binomial theorem, and it literally just is this weird expansion thing where you end up with, like, if this is to the 10th, I'm going to end up with that many terms, and it's going to be horrible. Good old Pascal's triangle. So yeah, we're not playing with that. That is why everything at this level, that ain't gonna have a sign in between. If it had a sign in between, you can't just distribute. You have to do something giant and horrible, and you're not gonna like it when you get there. If you get, I don't know. I think that's, is that in college algebra? I don't think it's in college algebra. Well, it's not in trig. It wouldn't be in calculus. Well, college algebra is pre-calculus, and I don't know why. For some reason, the college has a college algebra class and a pre-calculus class, and I'm like, all of the pre-calculus classes usually have a book that says college algebra on it. I don't know why there's a separate class now. I have been out of the loop for so long. I have no freaking idea, and it makes me angry. There's the same concepts. Yeah, it'd be in 126. It would have to be. And it's annoying for one whole time, and then you never do it. So yeah, that does have to distribute. You do it almost like they're separate problems. A squared to the 10th. Okay, that's saying I have this that many times. A to the 20th. B to the 5th to the 10th is B to the 50th. A and B don't go together, so that's it. That's all we got to do. Just multiply that 10 onto each one separately. Okay. I think there's another one. There's another one. Yeah. I do like this problem with the 5s, don't I? Parentheses, 5 squared, another starting parentheses, 25, close parentheses twice, squared. Why did I say it out loud that way? Because when you get really good with a graphing calculator, you start counting how many parentheses you open and close. And that's also a very useful skill if you don't want to do a ton of math and you want to let your calculator do. You could absolutely type this into a calculator in this exact way. And it's going to not give it to you in exponential form, but it'll give you your number. So again, I'm going to go with ignoring the outside parentheses and just looking at this stuff, right? And that we've already seen. I don't know why I'm putting an equal sign there. I like going down. Okay. So I'm leaving that alone. Inside, first, I'm going to change this to a 5 squared. And then I'm going to have a step where I put those together, right? So I have 5 squared times 5 squared. That's 5 to the 4th. Those go together nice. And now I have something to a power. To a power, it's exactly like our original example. We just have that thing with the powers multiplied together, 5 to the 8th. Which is probably a really big number that I don't want to mess with. Okay. So we feeling good on this? Like exponents?
Yes.
I'll take it. I'll take it. I was kind of hoping I could draw out exponents a little longer because I don't have these slides in the right order. Oh my God, I found my negative exponents. Well, I'm unhappy. Okay, so I thought we got to roots too. I knew I had examples with negative exponents. I just lost them, but I found them again. Look at that. I'm going to go ahead and skip the explanation slides because I've already talked to you guys about how negative exponents just jump to the other side of a fraction bar and become positive. So let's just look at the problems and play around with them. And the whole goal here is just going to be get positive exponents. I wanna know why my slideshow's out of order. Okay. I'm gonna do the first four quite quickly. Because, as I've discussed, anything with a negative exponent will become positive if you flip it to the other side of the fraction bar. I like thinking of it that way because I hate that that's usually written as a separate rule if you have it in the denominator versus having it in the numerator. You don't need a separate rule. It's the same concept. This guy has a negative exponent. It's not in a fraction, right? So if I know it's going to have to flip to the other side of the fraction bar, I'm going to have to put it under a 1, right? Because I have 1 of it, and that's kind of, universal placeholder. So it just becomes positive when you flip it to the denominator. Exact same thing with number 2. It's not in a fraction, so we put it in 1 because it flips to the bottom and becomes positive. Doesn't matter how big your problem is. I could slap a 0 on the end of this. 2 to the negative 150. Oh God, what do I do? You don't worry about it. You just put it on the other side, call it good. And then if it's in the denominator already, guess what it's going to do? It's going to go up here. It's not over anything in particular anymore, so it's just a 7 squared. You got a negative exponent, move it to the other side of the fraction. You don't have a fraction, make it 1. There's the concept. That is easier put than any math book you will ever see that explains that concept. Don't know why they don't teach it that way. Let's do more. Click more. You just did half of them. Guess what? The rest aren't going to take that long. And when I thought I lost those slides and I made the big ugly problems, and not have to worry about making up a bunch of little problems, I didn't think I'd run across them. I could have skipped this, but hey, a little more practice never hurt it, right? Hey, you know what number comes after 6? Number 7. Not the number 8. I'm not thinking it has at all. Oh, and I actually have a legitimate example that I didn't cover conceptually. Never really problem. Not all about being it. Okay. So we got more. We got more, but they're a little bit weirder, right? Just a little bit. Because number 5 already has a number up there, right? So what do? Well, the concept with this guy stays exactly the same. That 3 over 2 to the negative third, that 2 to the negative third is going to follow the exact same thing I just talked about. You have a negative exponent, you flip it to the other side of the fraction bar and it becomes positive. So how do I write that if I already have a 3 there? Well, if right now it's being divided and I'm flipping it up here, it ends up just being multiplication. So everything, and this is just going to be another way of looking at it. This is the answer, but everything fraction-wise can be split apart as separate pieces. So you can think of this as 3 times 1 over 2 to the negative third. And think, okay, that rule applies to this part. And this is just kind of hanging out, right? So you can absolutely think of separating out your fractions that way. Kind of like that big ugly problem we did earlier, where we could separate them out and then put them back together later. Kind of the same thing. But it might be easier to think about if I pulled that 3 out and just worried about that part for now. Now, number 6, 2 things you could do, right? I've already been over my fancy way of doing it. I could look at it as standard way, top power minus bottom power. We end up with a negative exponent. And to deal with that, we flip and put that guy on the bottom of the fraction. The other way to do it is the way that I explained earlier. I could look at this as saying I have 4 7s here, I have 5 7s here. So 4 are going to cancel from each of these, and I would have 1 left on the bottom. So you could look at it that way as well. If you look at it that way, it's a lot less writing. That might be beneficial, it might not. Then we have number 7 over here. Now number 7 is the one I said that I realized that this isn't a concept I had shown you earlier. Now when it comes to my canceling way of doing it, it's really important when you're doing it that way that you have no negative exponents left. None. Because trying to think about mentally canceling negatives, that's going to make you dizzy. Let's not do that, right? So what I usually do, well, for now, let's do it the book way, right? We could do the exact same thing, top power minus bottom power. And if you do it this way, oh my God, be careful. Because you are doing top power minus the bottom power, you are subtracting that negative sign right there. You have to make it sure it's written this way. If you don't, you will lose the fact that subtracting a negative turns into adding. You will lose that. You will end up far in the negative where we're supposed to end up positive. Now, if I was to do this with my canceling method, what I usually do is the first thing I do, wherever I have a negative exponent, it just goes to the other side. So I have this 5 to the negative 5th. That's on top. It's going to become 5 to the 5th on the bottom. I have 5 to the negative 7th on the bottom. That's going to jump up to the top and become positive. And now it's something I could actually look at as saying, okay, I can cancel stuff, right? I could look at this and say I have 7 here, 5 here. So 5 cancel from each of them, and I would have 2 left. So if you decide that that is a method that you like, that is something you want to do, something you want to use in the future, then you absolutely must have positive exponents for it to work out nice. Otherwise, oh God, messes happen. Let's not do that. So number 8, I'm just going to do it the standard book way of doing it. Because we only have 2s and 3s, right? We got weird powers, but we have 2s and 3s. Now, you might say, hey, Ben, why is there a parentheses here, but not up here anywhere? Well, if there wasn't a set of parentheses there, how would I know that was being multiplied? I would either need a multiplication symbol, or I would look at that and say that was 23 to the negative 4th power. So that's why that guy's still in a parentheses. So I can't drop it because the 2 is multiplied onto it. Now, for our 2s, I have 1 right here, right? Okay. So top power minus the bottom power would look like that. Okay, no problem. All right. Now the threes, same thing, top power minus the bottom power. So we have to be very careful with our signs. Make sure you're subtracting that negative. Here, these are nice, they go together real easy. Over here, these go together as a plus. So 5 plus 4, we have 9. And I will tell you, for your future reference, nothing is going to accept an answer with negative exponents. No online math homework you're doing, no GED or high set test, not going to like that. You have to make sure anything with a negative exponent is going to jump to the other side of the fraction bar, and that's where you're done. How we feeling? We feeling good? Liking this? Feel like we gave up. Our brains turned off at least 10 minutes ago. All right. It's hard to have a 2.5-hour math class and stay, conscious the whole time. You have my respect. Now, I totally wouldn't have been able to pull it off. I would have lost my mind. Oh wait, I did lose my mind, but completely unrelated. So, cool with exponents? We like exponents. We ready to do something big and stupid with exponents? Scientific notation. Everyone loves scientific notation. That's a lie. People get confused on this a lot. It's great. So the idea here is that scientific notation is just a term for I'm really tired of writing all these zeros. That's really it. Because think about what happens when, say I have a 5. What happens if I multiply that by 10? Well, now I got a 50. What if I multiply it by another 10? That's 500. Another 5,000. Another. So if I look at that 12 there, that's 12 trillion. We don't like writing that many zeros, right? That takes a while. It takes a while, and if I'm doing math with it, then it's weird and ugly and time consuming. And then I'm stressing about losing all those zeros. So the whole idea with scientific notation is that it's a way of reformatting our numbers by taking advantage of the fact that multiplying by a small number by 10 just adds a 0, or dividing a number by 10 kind of pushes it to the other side of a decimal. 30 nanometers, 0.00 blah, 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 3 meters. That's not fun. Not fun to write. It'd be really nice if I could just do 3 and then remember how many zeros there were. That's pretty much the concept of scientific notation. So I gave this very simple explanation of how to write scientific notation, its own slide, because, well, I like to stress what I see people make mistakes on, and this is a big one that people make mistakes on. So scientific notation is always written into parts. So you have just the digits that matter. So you had, say, like 214 or something. You always have the decimal point placed after that first digit, so like 2.14. And then it's always times 10 to a power. That times 10 to the power is our shorthand of, hey, this would be bigger or this would be smaller by however many places. That's it. So the times 10 to a power is just moving the decimal around, and the digits, you always have the decimal point after the first digit. So for example, right 0.0000000000436 in scientific notation. Why would I do this? I really hate writing that many zeros. So in scientific notation, the number part, as opposed to the 10 to a power part, has to be 4.36 because you need the digits that matter, which would be 436 in this case. And you always have to have the decimal after that first digit. So we know that we want to take that decimal point and shift it to the right past that 4. So usually you just put your pen on the decimal and kind of make those little jumps that you can see in the middle of the screen there. Make those little jumps and you count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then getting right past that 4 brings you to 11. And you're like, okay, I have moved it to the right 11 times. Now, I have personally always had trouble with these things being explained. If you're moving to this side, add, if you move to this side, subtract, and then if you're taking it out, it's the exact opposite. And that always made me kind of dizzy. I didn't like it. So what I do is I just conceptually think, okay, if you have a negative power on that 10, that is telling you that is a very tiny number. Because what does a negative exponent mean? Well, negative exponent would flip to the other side of a fraction, right? So if I have 1 over 10 to the 11th power, that's 1 over a really big number, right? So if I have 4.36 over a really big number, you know, if I describe my bank account as having 1 out of $1 billion, I'm sorry, I don't have $1 billion. I have 1. That's a tiny number. So you have that negative exponent. That is telling you this is a small number, so you have to have that as a negative. So going the other direction, converting it a number from scientific notation to decimal. This is where you literally just undo it. You do exactly what we did before in the other direction. So you look at that negative exponent and say, okay, this is a tiny number. So if I'm putting this back into standard notation, the decimal would have to move to the left, right? To make it a really tiny number. So you take the decimal point where it is between that 4 and 2, and you move to the left 7 times, right? So you kind of start off there between the 4 and the 2, and you start jumping it. 1, 2, 3, 4, 5, 6, 7. That's where you put your decimal. You call it good. Okay. Now I put this slide here because for most people, it is easier to think, okay, go to the left, go to the right, blah, blah, blah. So I did try to get that to kind of click in my head. Totally didn't work. But I can keep referencing it for those who it does work for. So when the number is 10 or greater, the decimal point has to move to the left. The power of 10 is positive. To convert back to decimal with large numbers, that decimal point has to move to the right. Right? Because it'd be getting bigger if I push that decimal to the right. When the number is smaller than 1, so you got that little fractional decimal thing going on, the decimal point has to move to the right. So the number, the power of 10 is a negative. Right? We convert back to decimal with small numbers, it moves to the left. Does that seem like something you can commit to memory? I can't. I hate that. I don't like that explanation. That's literally why I think, okay, big number, positive exponent. Small number, negative exponent. And you just know where the decimal moves if you're trying to make the thing big or you're trying to make the thing small, right? If it's small, you're all the way there past the decimal. If it's big, you're all the way above the decimal. That's pretty much how I think about it. Okay. So, say 13. Let's just do a couple. We definitely don't have enough time to do all of them. Let's just do a couple. The rest we'll do as part of the review next time. So I'm just going to put an asterisk by the ones that we do. I'm going to do number 2, and I'm going to do number 6. Very loose. Okay. 2, we're converting to scientific notation at 1, 2, 5, 3, and 8 zeros. 6 is a lot easier to write. 5.3 times 10 to the negative 7th. I can't make a mistake there. Can't randomly add or subtract a 0. Good stuff. Okay. So we got that thing. And we need to convert it to scientific notation. So what you always want to do is you want to say where your decimal point is now. We don't have one, but any solid number, it's kind of implied to be at the end, right? Okay. So we know that guy needs to go over here. My first thought is that if this is going in scientific notation, what sign is my times 10 to the power going to have? Is it going to be a positive or is it going to be a negative? Well, big number, right? So positive. Because I'm multiplying by that many 10s. There's a 10, there's a 10, there's a 10, there's etc. That's literally all this is just chopping off a bunch of 10s, right? So what we do is we take that decimal point, start jumping and counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we got 11 jumps. Okay. So we're going to be at 1.253 times 10 to the power of 11. That's it. That's all we got to do. Not bad, right? Pretty tolerable. And then going the other direction, number 6 here. We have 5.3 times 10 to the negative 7. Okay, so times 10 to a negative power, this is telling me that this is a small number, right? Now look at that negative exponent, and I'm going to say that's a small number. So if it's a small number, where's that decimal point going to go? It has to go over here, right? Because make that guy tiny. If I moved it over this way, then it would make that a large number like this guy. But since I have a negative exponent, got to go in the direction to make it a tiny number. So what I do, give myself a little bit of room to the left because I know that's where I'm going. And I'll put my pen where the decimal should be. And I'll just start counting. 1, 2, 3, 4, 5, 6, 7. Right there. What do I do with that? Fill in every one of those jumps with a 0. You always kind of want to have a 0 point something on these. You always kind of want to have that implied like number to the left of the decimal. but then everything to the right is exactly as described. 1, 2, 3, 4, 5, 6 zeros. That 5 is where it jumped from afterwards, so that's our 7th power, and the 3. So we end up with 0.00000005. Okay. How do we feel on this? It's gonna be a lot more fun next time when we're adding, subtracting, multiplying, and dividing these. Yeah, those are fun. Those are fun. They're actually really, the adding and subtracting is annoying. And I literally only have it in here because I realized that I've never really seen a whole lot of it. Multiplying and dividing is surprisingly easy with these. Surprisingly easy. So I definitely don't have time to hit either of those concepts tonight. I just wanted to give you guys a little taste of this for now. We'll do more of this when we come back on. All my days are running together. If today's Thursday, it's going to be Tuesday. If today's Tuesday, it's going to be Thursday. Next time. I don't even know anymore. So, yeah, how do I end the class? I never did figure that out. Socially. Very socially awkward. We're done. I'm calling it. We're done. I'm happy with this. You guys happy with this? Have a good night, everyone.